Let's take a look at the homework on page 235. And on this page, we're really putting together a lot of ideas from mysteries of the first and second derivative. We're going to be given some information about first derivative, second derivative, and we're going to have to synthesize those ideas, think about them, analyze them, and sketch a graph that meets certain criteria. So these are really, really good problems. I hope that you spent some time trying to figure them out before you let me figure them out for you. But I do hope this video helps you to learn how to think about these things. So let me grab a pen here. So the first problem we're looking at is number 59, and I know I have the answer over there, but let's go ahead and read, break it down, synthesize it, figure it out. Consider a function f. So we are thinking about an original function, and here come the criteria. Criteria number 1 is the first derivative is increasing. Not the first derivative is positive, but the first derivative is increasing. So your job is to think, okay, what does that tell me? If the first derivative is increasing, and you might have to look at your notes at this point to remember, if the first derivative is increasing, f original is concave up. Go back and look at your notes on concavity. The first derivative can reveal concavity if we know about the graph of the first derivative. So if the first derivative is increasing, we're trying to graph a function that's concave up. All right, so we have one criteria. Sketch graphs for f, so we're trying to, again, sketch a graph of the original function. For a, the first derivative is less than 0. So I have to interpret, what does it mean for the first derivative to be less than 0? So now we're talking about positive, negative. If the first derivative is less than 0, f original is decreasing. So that was my second criteria right here for A. I'm trying to draw a graph that decreases, goes down, and is concave up. So if I want a graph that goes downward and is concave up, I'm going to draw in number 59 something that looks like this. The graph is decreasing. This is my original function f. So decreasing and concave up. For letter B, they are asking us to draw a different graph, and this time the first derivative is positive, meaning that f original is increasing. So when you read these statements, you really want to begin by doing this work right here of thinking about what is this really telling me, maybe even writing it down. So now I want a graph that is increasing and concave up. So this graph right here in purple increases, and it is concave up. So that is what a graph of f could look like based on this criteria. All right, let me clear the annotations and let's go to number 60. So we're doing 59 through 61. All right, let's do the same thing with number 60. So again, we have a graph of an original function, so the graph of f, that's what we're focused on. This time, f prime, first derivative, is decreasing, which tells me that f is concave down. We're going to do the same thing for the second part. So we're going to have one graph where the first derivative is less than 0, which means that f is decreasing, and the first derivative is greater than 0, which means that f is increasing. All right, so let's take a look over here. So the first graph, we have concave down, decreasing. Concave down, so right here, concave down and decreasing. The graph is clearly going down, and it opens downward, so I'm concave down, decreasing. Second criteria was concave down, increasing. So the graph is increasing, getting bigger as we travel from left to right, but the graph is also concave down. So that's number 60. Let's clear that and go to 61. In number 61, we are sketching the graph of a function. It's always about the original function that does not have a point of inflection at CF of C, even though the second derivative is 0. So let's think about the second derivative being 0. So look at I think I do a pretty good explanation here. If the derivative, so think about a linear function. The derivative of a linear function is constant. So for example, let's make up a linear function to see what I'm thinking about here. So if I said, let me think about f of x equal to 5x, there's your AP score. The first derivative of 5x is the constant 5. The second derivative of 5x is 0. So that meets the criteria that they asked me to deal with over here, is that the second derivative is 0, but I don't end up with a point of inflection, because if I graph the line y equal to 5x, it might look something like this. So there's a linear function. The second derivative of that linear function is always 0. There's no point of inflection because there is no concavity change. In fact, this line does not have any concavity. So that's what I chose for number 61. You might have gotten creative and thought of something else, but you can certainly ask me about that in class. All right, we're not doing those items down there. We're going to number 67, which again is interpreting this information. I would encourage you to do 67 through 70. Maybe I'm going to assign them in a different assignment. Maybe that's why they're not in this particular one. But in number 67, we have all these criteria. So we've got to make all of these things happen on one graph. So I always begin with the easiest thing first. The first thing that I notice here is that they're just giving me that two x values with the same y value. So f of 2 is equal to f of 4 is equal to 0. That makes me happy because that's easy to plot. So I'm going to come over here to the graph that I created. So f of 2 is 0, so I would plot that point. F of 4 is 0, I would plot that point, and then I would check that off to say, yep, that's done. The second item says f of 3 is undefined. So I would say, that's going to give me a question mark right there. If f of 3 is, f of 3 is defined. Wow, did I really misread that? F of 3 is defined, so I'm like, I'm not sure how that's going to manifest itself, but okay, that's just telling me there is a y value at 3. Now, the next piece of information, these three pieces of information right here, so 1, 2, 3, notice that they are all about the first derivative. First derivative, first derivative, first derivative. So I'm going to transfer that information to a first derivative number line so I can see with my eyes. So the first bullet says the first derivative is negative to the left of 3. Then it says the first derivative does not exist. That's important at x equal to 3. So that tells me I have a critical number at x equal to 3, which goes on my number line. In bullet 1, I just said to the left of 3, the first derivative is negative, and that tells me that the original function is decreasing. To the right of 3, the original function is, the first derivative is positive, so that's on my number line. So the original function increases. So I have a function that decreases, and I have a function that increases, but it's important. The second derivative is not defined at x equal to 3. But look right here. See, it's all coming together now. The y value at 3 is defined, so that's blocking me from a vertical asymptote. That's blocking me from a hole. However, the first derivative does not exist at 3. So if I'm blocked from a vertical asymptote and I'm blocked from a discontinuity, then my only option is I'm going to either have to cusp or sharp turn to make the derivative not defined there. So I know I'm going to have a cusp or a sharp turn. And then lastly, I'm going to go to my last statement, which is all about the second derivative. So this says the second derivative is always negative except at 3. So 3 is going to be my possible point of inflection, but it's not going to be a point of inflection because the second derivative is always negative, which means the graph is always concave down. So that reinforces this cusp or sharp turn. So the graph that I drew meets all the criteria. So in region 1, to the left of 3, the graph is decreasing. So yay, that worked. The graph is concave down. That worked. The first derivative is not defined at 3. That worked. After 3, the graph increases and is still concave down. So those criteria force you pretty much into this one graph. I can't think of anything else that would meet the criteria. All right, that's 67. Let's go to number 69. Same deal. In number 69, I'm going to begin with the most obvious. F of 2 and F of 4 are both 0. So there's F of 2, there's F of 4. That was easy. I like when the work is easy. The second statement is about the next 3 statements are about first derivative. So that information I'm going to transfer out of symbols and onto a number line. The first derivative does not exist at 3, so that puts a critical number on my number line. To the left of 3, the first derivative is positive, so that's what I have here. To the to the right of 3, the first derivative is negative. That's here. So I have a graph that increases then decreases. All right, let's keep going. Now this time they don't tell me that there has to be a y value at 3. Nowhere does it say f of 3 is defined. So I'm going to go to the last piece of information. The second derivative is always positive, which means the graph is always concave up. So I want to increase, I want to decrease, and I want to always be concave up. The first derivative is not defined, so now I can have a discontinuity, or maybe I can have sharp turn or cusp. So all of those things are open to me, but in order to make the increasing, decreasing, and the concavity work, I decided to put a vertical asymptote at x equal to 3. So there's my vertical asymptote. And then the graph is supposed to be increasing. Let's change colors here. Increasing on region 1. I'm just looking at my number line, and we're supposed to always be concave up. And then I'm supposed to be decreasing, and the graph is always supposed to be concave up. So I have concave up and concave up. So these are not hard. You just have to keep playing with them and making until you get the graph that meets all the criteria.